Are you ready, Sara? Let's start.
Yeah, sure.
Okay, good morning, good afternoon, and good evening. Welcome you again to this World River and Delta System Source to Sink webinar series. Today, sorry. Okay, so today we are very happy to invite Dr. Sara Morón from University of Sydney, Australia. Now she's still in Australia there, and now it's 11 p.m. And thank you very much. Agree to contribute a talk for this series. So her talk will talk about ups and downs of continental-scale deltaic depocenters. So before I introduce Sara, so I will mention this coming Friday, landing Domingos from Brazil coming here talk about the famous wave-dominated river delta San Francisco system and how the sediment all the way from the river to the delta and all the way to the canyon to the deep sea. As you can see, very beautiful work. So please mark your calendar. And Sara, as I mentioned, now in University of Sydney is a research associate. Originally, she got her bachelor degree from National University of Columbia. And then later, she went to University of Minnesota, get a master's degree, and then went to Australia, University of Adelaide, get her PhD. And so I will point out, she also got a Fulbright fellow, will coming here to Caltech soon, hopefully later this year, as a visiting scholar in US. Her research is use software, modeling geochemistry and field data to understand how and why the river evolves through time and space. As you can see, what control the river style and what do and tectonics control the river elevation, and how do the plate tectonic play the role in the river, the lifespan and scales. So her work is kind of like a global scale, continental. So Sara, now you can share your screen. So we're looking forward to your talk.
Yeah, great. Just give me a second. Let me see how I go.
Yeah, now it looks good.
Great. Okay, so greetings everyone. Thank you for inviting me to this amazing series about source to sink systems. And as Paul mentioned before, it's 11 p.m. here in Sydney, so I hope I stay awake. But yeah, thanks for coming. And I guess I just wanna also mention that, yeah, the research that I've done in the past also encompasses the understanding of river styles, and I've been working with river systems at different scales, so in time and space. But the work that I'm going to be presented today is more about continental-scale deltaic depocenters. So yeah, and today I'm going to talk about how flexural isostasy and sea level change can control the evolution of deltaic depocenters. Flexural isostasy is particularly important for deltas located in passive margins, where a large component of the subsidence is not related to tectonics. And I've been exploring these concepts with numerical models, and of course with the help with a large group of people who include Mike Bloom, Tristan Saul, Roman Boucher, Stephen Gallagher, Louis Moresi, Rebecca Farrington, and Claire Mallard. And all this research has been developed under the umbrella of the Basin Genesis Hub, which is a 5-year project that is producing new technologies to better understand the evolution of basins. Yeah, so I guess for those of you who are not familiar with the lithospheric dynamics, flexural isostasy is the deflection of the Earth's lithosphere in response to loading and unloading. So in this case, as you can see here in this cartoon, I have a, when the load is imposed over the lithosphere, it creates this deflection. And then on each side, you will observe something called a bulge. So in the next couple of slides, and then of course, once that load is retrieved, then you generate uplift where there was subsidence before. So in the next couple of slides, I'm going to show you examples of how flexural isostasy plays an important role in source to sink systems. So for example, the effect of isostatic adjustments in fan deltas has been investigated in the Amazon, and that's work has been published by Watts extensively. But I think that one of the papers that synthesizes very well the effect of isostatic adjustments in fan deltas is the one that he published in 2008. And what that study showed is that if you take into account the large volume of sediment that has been deposited in the river mouth and the fan delta, and then you calculate the isostasy that load creates, more than 2 kilometers of flexural subsidence over a distance of 500 kilometers have been created. And yeah, that's also kind of shown here in this map view. So again, if you calculate the flexure of that load, you can see how the contour lines in this map show the subsidence and the deflection that has been created. And then if you see it in a cross section, so this cross section has distance on the x-axis and then topography on the y-axis. And as you can see, so that the dashed lines and the red lines are different calculations of how much flexure that load would have created in the Amazon margin. But then if we look also on a larger scale, we can see that the effect of flexural isostasy is also important in the drainage reorganization, and in this case, for example, of the Amazon catchment. So the scientists from this expedition that was going to go ahead before COVID, but has been postponed, have proposed that the isostatic uplift of the shoulders of the rifted margin of the Amazon, so the Brazilian margin, as you can see those red lines that I've shown here, these remnant rifted shoulders, probably also triggered and helped the reorganization of the Amazon River. I mean, of course, we know that the uplift of the Northern Andes played a role, but then on top of that, it seems that the remnant of those arches and the ups and downs of those arches related to isostasy have also helped to change the margin and the drainage organization of the Amazon. And then if we go to the Mississippi River or the Mississippi catchment, there was this study published by Andy Wicker in 2009, where all the co-authors proposed that the Mississippi, the catchment of the Mississippi changed due to the effect of glacial isostatic adjustments. So they proposed is that when there was ice, then this ice, large ice volume over the North American continent created dams on the one side of the drainage divide. And then that created the ponding of the waters into lakes that then were, once the ice retreated, then that caused the glacial fluvial erosion. And once that forebulge collapsed, then that filled the alluvium and also integrated the entire drainage. So they calculated that at least 65 meters of incision was created because of the quaternary sea level fall. And then also staying in the Mississippi, there was this study by Mike Bloom that was published in 2008 and a follow-up in 2013, where isostatic modeling shows that sediment volumes removed and replaced during glacial and interglacial cycles were sufficient to induce uplift of 9 meters along the valley margins. And then, of course, once you remove that material, you also get, once you add that material, you get subsidence of the same magnitude. And those effects dissipate over distances larger than 100 kilometers along the Gulf of Mexico. And then that similar effects have been also observed in deltaic margins, like in the Bron deltaic margin, for example, where the impact of water loading on the vertical deflection along the platform has been observed between low sea level and interglacial high level stages. And yeah, that was concluded based on very detailed seismic data and numerical modeling. Okay, so now that I've given you a brief overview of how important flexural isostasy is for fluvial deltaic systems, I'm going to now tell you what I'm going to be focusing on in this talk. So during this talk, I'm going to explore the following questions. So how do flexural isostasy and sea level changes control the evolution of deltaic depocenters? I'm going to be exploring if flexural isostatic adjustments can be of high frequency and bidirectional, and if there is a direct response of the flexural isostasy to the low partitioning due to climatically driven sea level changes. Oops. Sorry, I'm just having a little trouble with the mouse. Okay. So it turns out that there is this widely accepted view that flexural isostasy has a, or at least in deltas, that it has this unidirectional behavior. And to illustrate that, I have this cartoon that shows that there is an increase in subsidence as the sediment load increases through time, right? So to illustrate that, I have here T1, T2, the last stage of the formation of a delta. And yeah, of course, as you can see, the flexural deflection increases through time as you add more load. So yeah, people usually tend to think that that flexural isostasy is completely monotonic. However, we know that also there is a correlation between sediment partitioning and sea level changes. And to illustrate that, I have this cartoon. So the thing is that during, as you know, high level stands, the sediment load will be deposited closer to the shoreline. While in low stands, the sediment load will be deposited closer to the shelf edge. So one would expect that because the load is imposed in different parts of the margin or the shell, then that flexural isostasy will also change in space and time. So in order to explore that question, I did a series of set of simulations with synthetic sea level curves of different frequencies and amplitudes. And then the other question I have is whether there is a direct response of the flexural isostasy to the low partitioning due to sea level changes caused by or induced by climate change. So in order to do that, I imposed simulations, or I did simulations where I imposed sea level curves from polar free and polar ice dominated periods. And then I compared them with a suite of non-flexurally compensated models. So yes, the code that I'm using today is called Badlands. Yeah, so you can know more about it if you go to this repository, which is in GitHub. For those of you who are not familiar with GitHub, it's one of the largest code repositories in the world, and it's open source, and so you can access the repository, and it has a lot of tutorials, and you can have a lot of fun with it. Yeah, so the code was developed by Tristan Sal, and it focuses on solving basin and landscape dynamics. So it simulates hill slope processes, fluvial incision, sea level fluctuations, and it also uses GFlex, which is a code that solves for the elastic plate flexure. In the simulations that I'm showing today, I'm not accounting for compaction, submarine gravity currents, grain sizes, or tectonic subsidence. The reason for not accounting for tectonic subsidence is because, as I mentioned before, in passive margins, the tectonic subsidence component won't be as significant as the flexural component. And I also don't want to introduce more noise because I'm only focusing on the role of the flexure, and I want to be able to tease out just the flexural component. So yes, the model setup. So the model setup, the initial configuration of the modeling domain resembles the topography of a natural source scene system. So as you can see, there is relief on the headwaters, and then that, of course, the slope changes to a continental plane, and successively changes the gradient to a continental shelf and the continental slope. And that is also shown here in this longitudinal profile of the whole domain. And then right at sea level, I can impose sea level changes like the ones that I'm showing here in this plot. So for these simulations, I'm using an elastic thickness that is of 50 kilometers. So that reflects how rigid or non-rigid the lithospheric is. But so that is in a range of passive margins. I also did a comprehensive sensitivity test with different elastic thicknesses, but because I don't have time to go through it in this talk, that's why I'm not showing the results of that sensitivity test. And the temporal resolution of the simulations are around 100,000 years. And that is to, of course, capture the changes that I'm interested in. But if I wanted to investigate the smaller temporal changes, I could also change the resolution. Yeah, so this is how the results, or like how the numerical models, when they have evolved through time, look like. And I'm just going to have a sip of water. So as you can see here, there's a catchment with the headwaters, and then there's a deltaic plain, and then the marine component of the modeling domain. And then the great thing about Badlands is that then you can also extract information about the flexure, and that is what is shown here in this bottom plot. And then the other great thing is that, so although these are conceptual numerical models, they're all based on scaling relationships that we observe in nature. And to demonstrate that, I have this plot here, these two plots on the right-hand side of the slide. So as you can see, here on the x-axis is catchment area, and then on the top we have length of the longest river channel. And so what I did was I plotted, thousands of data points that are from all these compiled data sets. And as you can see, and then I measured or I calculated those metrics in my simulations. And as you can see, they are in agreement with the natural cases that we observe, or metrics from natural examples. And it also shows that these river systems that I'm simulating are as large as or at least in the same order of magnitude of the catchments of the Paleo-Mississippi River. So then the same thing for shell width and catchment area. I use this data set published by Bloom and co-workers in 2013. And as you can see, the shell width also scales with the same relationships that we see in nature. Yeah, so I'm just going to show you one example of how one of the simulations evolves through time. So as you can see, this is the plan view, and I just zoom, I've zoomed in to the where the continental and the marine realm meet, and so that's shown by the color bar here. And then I'm going to also show discharge, how the discharge changes through time, and then the thickness. So the thickness of each of the time steps. And then remember that in this interface, so in the land-water interface, land-ocean interface, I should say, that's where the sea level has been imposed. And I'm going to let that play. So as you can see here, oh, and I forgot to say, sorry. As you can see, for the first 2 million years, there are no sea level changes because we want the system to reach steady state, or at least to give the time for the system to reach equilibrium. And yeah, as you can see here at the bottom, it's also showing how the stratigraphy builds up through time. So as you can see, the river mouth is moving back and forth. Then the deltaic depocenter is building through time, and that is being recorded in the stratigraphy right here. And then you can also see how the bulge and the flexural isostasy is also taking place, and that's why we have this beautifully shaped clinoform. Oops. Okay, so now I'm going to show you the results of the simulations. Yeah, so the result of the simulations show the evolution of the catchment and the deltaic depocenter. So on the left, I have this cross-section that shows how both the catchment and the deltaic depocenter change through time. So this is the time reflected in millions of years. So as you can see, blue colors indicate the beginning of the simulation, and then the brown colors, the end of the simulation. And one of the things that is, so on the top panel, I'm showing the longitudinal profile. So of course, that's showing elevation and bathymetry. Then on the second set of panels, I'm showing the erosion deposition. And then on the third panel, I'm showing the flexure. So remember that I have models that I ran with flexure, and then or set of models that I ran without the flexure. And I want you to notice two things, which I think are really cool. So in the flexural cases, in the cases with no flexure, the shelf migration it goes farther into the basin, as you can see here. So that's why I'm showing those dashed lines. And then on the second panel, you can also see that in the models without flexure, there is less erosion and less vertical accumulation. And the reason for observing less erosion is because, of course, there is no rebound, no flexural rebound, and no uplift here in the continental domain. And then, of course, because there is also no deflection and subsidence, then that's why there is also less vertical accumulation here in the model. And then the third panel, this is just showing the how the flexure evolves through time. So we have the rebound in the continental domain, and then the subsidence in the marine part of the model. So on the right-hand side, I have a long strike cross-section. And again, so in the left, I have the results with flexure, and then on the right, I have the results without the flexure. So in the first, the top panels, it's really interesting to see how the simulations that have no flexure don't have any flank uplift, right? Whereas in the flexural cases, you can see how you have that bulge that is created as the load is being imposed. And then, of course, because there is less accumulation being created, in the cases with no flexure, there is less vertical accumulation. And then, of course, here, as you can see, there's this beautiful graph showing how the flexure evolves through time. So the interesting thing is that then if we look at data from the deltaic depocenter of the Mississippi catchment or river, you can see some similarities. So it's not just that I'm making stuff up and that I'm just believing in what my models show, but so for example, in here in the left bottom corner, I have these cross section, so a long strike cross section, and this cross section is based on the Phelan data set that was published in 2016, and the data set is based on thousands of points, and they are chronostratigraphic peaks. So it's really good because they reflect time, just like my simulations. They do not reflect changes they're not based on seismic data, and they do not reflect changes in lithology. They reflect time peaks. So they are timelines for 65 million years, which is super cool. So as you can see here in this cross section, there is also this like flank uplift or this bulge, again created by the rebound and the difference between the load being imposed here, and then that again that uplift created on the sides. And then in here you can also see, of course, how as you have more sediment load being imposed, you have more space or more infill being recorded in the stratigraphy. Okay, so how then the next part of the talk is going to focus on whether flexural isostatic adjustments can be of high frequency and bidirectional. So for to address that question or explore that question, I created a set of simulations with synthetic sea level curves with different frequencies and amplitudes. So yeah, to show that I have these plots here. Oh, and I don't know why the resolution is not that good. Apologies for that. What I have, oh, so I should mention, sorry. The results I'm going to show right here, right now, are measured right on the river mouth at each time step. So on the x-axis, here I have sea level, then in the second plot, flexure, and then on the third plot, the river mouth trajectory. So like, how is the river mouth migrating? Yeah, so then as you can see, so in this case, I have a sea level that is constant, is not changing. And what is interesting is that the flexural isostatic compensation is monotonic and is only observed if the sea level change is not considered. Whereas when I then impose different sea level curves with different frequencies, as you can see here on the second panel, so that has a frequency of 5 million years, and then this one, the bottom one, has a frequency of 500,000 years. And what is really interesting is that the flexural isostatic compensation, as you can see, is in sync with the frequency of the sea level changes. And there is also a direct response of the flexural isostatic compensation to that sea level change. And I forgot to mention here, sorry, that the dashed lines on this plot are for the measurements of the river migration for the simulations that do not have any flexure. So and that, I guess that those results that I showed you before are just not visual. We actually carried out spectral analysis. And so we looked at the frequencies of the sea level, the flexure, and the deposition. And as you can see, they are all in phase. So on the x-axis, I have the frequency here. And as you can see, so the peak of the simulations that had 5 million year frequency, they correspond. And then the same thing with the simulations that have the 500,000 years. And then the other thing that we did was we extracted the stratigraphy and we created these Wheeler diagrams. So for those of you who are not familiar, Wheeler diagrams show how the stratigraphy changes or how the position changes in time and space. So time in the y-axis and space in the x-axis. For this Wheeler diagram, I picked a cross-section that was right in the middle of the modeling domain. So on the Wheeler diagrams on the left are the ones that have flexure, and then the ones on the right are the ones that do not have any flexure. So as you can see here, in the ones that where is the no sea level change, we have a normal regression. But then the ones that have where the sea level changes, then we see that there is oh, sorry, and I forgot to say, the color bar shows the bathymetry. So in this case, it's not lithology, it tracks the bathymetry at which the sediments were deposited, with green colors being shallow and then blue colors being deep water deposition. And then the interesting thing, and then of course the white spaces show hiatuses. So what you can see is that there's incision during sea level fall. So we have forced regressions, and that's here highlighted with the gray shades. And then the incision is further into the basin as the sediment load increases with time, as you can see, of course. there is that that trend over time. Yeah, so I hope I convince you that this data shows that there is an interplay between the flexural isostatic compensation and the sea level change, and that controls same and dispersal patterns, and of course the accumulation of sedients. So we did the same thing for simulations where we changed the amplitude, and that's what you can see here on the left. And one of the things that is really interesting is that there is a 30% difference in the flexural response, depending on the amplitude, right? So like to show that, I have some box plots here for simulations where we only impose 10 meters of amplitude, 25, and 100. And of course, that is related to the fact that there is also a hydrostatic component of the isostasy. And then the third part of the talk will focus on exploring the question if there is a direct response of the flexural isostasy to the load partitioning due to climatically driven sea level changes. So yeah, remember that for that, I used a series of simulations with sea level curves from contrasting climatic times, so greenhouse and Icehouse. And that's what I'm showing here. So on the top, we have the sea level curves that are representing Icehouse events, and then on the bottom, greenhouse events. And then again, so sea level on the first panel, then on the second one is flexure, then the river mouth, the distance. So how is traveling the river mouth from inland to the shelf. And then the stratigraphy represented by Wheeler diagrams. So of course, the two different scenarios, so the greenhouse and the Icehouse, have different same and accumulation patterns as expected. And as you can see, there are more periods of erosion in the Icehouse as in the, because the sea level is low and the shelf is exposed. And of course, we carried out the same simulations, but without taking flexure into account. And then again, as expected, there are more periods of erosion in the flexural, in the non-flexural cases, as they, sorry, there's a typo here, as the non-flexural cases, as there is no vertical space being created. Oops. So then the other thing that we wanted to understand is, because we saw the difference in the river migration, we wanted to see how that was reflected, or like how that showed in the delta morphology. So as you can see here, we have the plan view of 3 of the simulations. So one without sea level, or sorry, with sea level being constant. Another simulation where we impose the 500,000 year cycles, and a simulation where we impose the 5 million year cycles. And then, so the top panel is with flexure, and then the bottom panel is without any flexure. And as you can see, there is a difference in lateral extent, elevation as well. As you can see here, there is a higher topography in the cases with flexure because of the flexural rebound, and the river mouth morphology between these two cases. And of course, that is to do with the fact that there is no vertical space being created on the cases with no flexure. So the other thing that we measured, or like we tracked, was the position, so the XY position of the river mouth through time. And that is for the three synthetic examples, the Icehouse and the greenhouse. And we also measured the, so we measured the distance of how far this river mouth was from the shelf break. And we counted the frequency of how many times that occurred. And as you can see, there is a large percentage of that, or there's a higher frequency that we see when we don't have any flexure, right? And the other thing that we wanted to investigate, or we wanted to understand, was what was happening when there was a change between high stand and low stand. So this is one example of the many simulations that we ran. And so in here, I have the sea level. And so we picked these two particular times where we have high stand and low stand. And as you can see, this is how it's shown. So this is a zoom in into the modeling domain. This is showing the elevation, the bathymetry, and then this is the lines here are showing the shoreline position. And then what we can see is that the net valley incision during sea level fall and the cross shelf extension of the river systems are different. And that is because during sea level rise, of course, there's a change in the rebound. So, and that can be shown here, where we can see the different positions and then the calculation of the flexure. And of course, that's in accordance with what previous studies have been shown for the Mississippi Delta and the Colorado River in Texas. Okay, so to conclude, the simulations that we ran and the examples that I presented show that the shifting of sediment and water loads driven by sea level change can result in a cyclic response of the flexural compensation. The isostatic compensation amplifies the vertical adjustments caused by either eustatic changes or climatic changes. And I hope I convince you of the importance of that amplification in subsidence patterns and the effect that that amplification has on delta stratigraphy. And yeah, so I also want to thank all the team and all the people who have worked in creating all these technologies that I'm using to better understand how basins evolve through time and space. And if you want to learn more about it, please go to bgh.org.au. Thank you.
Thank you, Sara. That's a great talk. And so as the audience, if you have any questions, so you can go ahead, unmute yourself and go ahead to ask. Tor, you have a question?
I have a question, yeah.
Sure. Go ahead.
Well, thanks, Sara. That was a really interesting talk. And I actually have several questions, but I have one really general question. So maybe I should just focus on that. And so the one thing that struck me is that a lot of your simulations show, very rapid responses to the sea level forcing. And, you talked, it looks to me like these are basically elastic responses that, are basically instantaneous. And you talked about the how you explored the parameter space around the lithosphere, but you didn't. I didn't hear anything about the mantle and different mantle viscosities and basically viscous responses that are slower. Did you look into that as well?
No, because the code that I use solves for those instantaneous responses. Yeah, so that, I mean, it is one of the limitations or one of the things that the code is focusing on. Of course, if you wanted to understand a more elastic response, then you will have to create a different set of simulations and use a different code.
Yeah, I mean, I see Mike Steckler is with us too, and I'm sure he has some way more thoughts about this than I do. So
yeah, so I guess that's one of the things that when I started this project, that's one of the things that I really wanted to investigate. And we started, or my big dream was to use this code that is called Underworld, and I wanted to couple that with Badlands. So Underworld is able to solve for the elasticity or viscoplasto-elasticity. But the coupling is very challenging, and being able to not just couple, but make sure that when you are pairing surface processes and mantle processes, that the answers that you get are accurate is a very hard problem. So I thought about it, but the technology is challenging.
okay.
And the numerics behind are very challenging.
Right.
Yeah.
I can add to that. Yeah. So, very nice talk. At the time scales that she's modeling of cycles that are, 5 million or 500,000 years, you can get away with an elastic response. When you go to higher frequency, sort of like the glacial frequencies, that's when you start getting in interplay. And I played around not with a full elastic, but allowing for sort of a time for elastic compensation to come into play. And if you start getting the frequencies of the cycles and the frequencies of the elastic responses being similar, you start getting a lot of lags and things that start affecting your stratigraphy.
Yeah.
So that would mean that it's less of an issue for greenhouse conditions, but when you move to icehouse conditions, then
right.
Then obviously, because you basically have to consider all the Milankovitch frequencies, and then it becomes a different story.
Right.
Absolutely. And that, yes. So I guess in that sense, I'm not focusing on the last Icehouse. I'm using more of deep time Icehouse periods.
Okay, thank you.
Thank you for your questions.
Okay, anybody else? So Sara, I think you did a very good job, see the sea level cycles, try to understand the stack of the depocenter change. But in reality, we know the controlling factor including sea level definitely number one, and tectonic, and also the flux of the sediment. The other point of view maybe is the wave, tide, and longshore current, because in many major river system, Amazon, Mississippi, Yangtze, Mekong, you name it, most of them, almost 30 to 50% of material was shipped away from the river mouth, and they was sending away alongshore. Not all the stuff really crossed the shelf, form that kind of beautiful, textbook sequence stratigraphy. So in the model, is any component to add that part? See how much after they deliver to the ocean, how much they will shift away, drift away, from that proximal depocenter.
Yes, absolutely. You are completely right. The model does not take into account longshore drift, and that is a significant component of delta stratigraphy. If you wanted to test that, you could do it in Badlands, but it will, again, it will be a different set of experiments because you will be testing the role of longshore drift instead of the interplay between sea level change and flexural isostasy.
Yeah. So is the model is extendable, right? Extendable, right?
Yeah. Yes.
Okay. That's wonderful. Maybe
I'm
we can
struggling to publish this one. So once I publish this one, then we can talk.
Yeah, we should add that module because sea level sediment, that's kind of like a two-way, a two-way. If we add a longshore drift, it will suddenly become a 3D dimension.
Absolutely, and that is something that I also think that plays a big role in the Amazon, for example, and that for the understanding where exactly the load is imposed and how that also is controlled by the advection of the sediment is very important.
Yeah. We all know Amazon drift away 1,500 kilometers.
Yes,
and the Yangtze Yellow River is all 800 kilometers away. So that's something very important component we cannot ignore. Okay, anybody else for Sara?
You can add that paper to the list, to the papers to write.
Keep me updated. Okay, Michael.
Yes, also like to ask, for the modeling, you used a 50-kilometer elastic thickness, which is very high for a passive margin, even for an old margin. But have you also considered, you did a comparison of no isostasy versus flexure. Have you also considered the comparison to a local isostasy or a very low elastic thickness to see that change as well? Because then you'd still get the loading, but it would become much more immediately under the depocenter.
Yes, yeah, absolutely. So I did a series of sensitivity tests where I ran the same simulation with different elastic thicknesses, and that's what I'm showing here on the screen. And those are cross sections, so along the strike cross sections at different distances from the river mouth. And as you can see, of course, the low TE, so the low elastic thicknesses have a smaller wavelength, as you can see here in the in the plots. And of course, the ones that have higher rigidity, of course, have a larger wavelength as expected. But I guess what is really important is that the overall trend is, I guess, that the results do not change dramatically in the grand scheme of things, right? So like the large scale changes that I'm focusing on have the same pattern. But yeah, I guess this is something that I didn't have time to talk about. But I mean, at the same time, if you wanted to be really, really accurate, you will actually have a thickness map, so a TE that varies through space. And that is something that is possible in Badlands, but I just didn't want to add more complexity to the model because I guess the model is complex enough that I wanted to fully understand the interplay between the flexural isostasy and the sea level.
You start with the simpler cases and then add the complexity as needed.
Exactly.
Okay. Cool. I think you've known any first question. Sara, thank you so much. I know it's almost midnight for you, and we appreciate it very much.
The is about to pick me up.
So I hope we will see you in United States, in US, and so everything hopefully after this summer, we don't have any rebound of
Yeah.
Thank you. Sarah, are you coming to Caltech? Whose group you are coming for visiting?
I'm going to be working with Mike Gurneys.
Okay.
And
Cool.
I'm also hoping I can collaborate with Mike Lamb.
Okay, yeah, Macallan, yeah.
Yeah,
Okay.
to try to again
Yeah.
couple the surface of the Earth with the lithosphere. So
Wonderful. Maybe you can use this to try to understand the sequence stratigraphy on Mars. You know what? You know,
yes,
like,
absolutely.
Mike is trying to figure out that.
Yeah, there are no limits. Cool. But yeah, thank
Wonderful.
you again for having me, and thanks for listening.
Sure, sure. Thank you. Okay. Before we go, okay, this Friday, you know, landing come talk about San Francisco, and he will talk all the way to the canyon. That's wonderful. We know it's a wave dominated river delta, but we don't know too much how the sediment go all the way to the deep sea. So coming back this Friday, same time. Okay, cool. Thank you. And I think on the chat, people say a great talk. Great. Okay. So see you.
Thanks for organizing.